Good afternoon, everyone. This section is 5.5, and it talks about U substitution. Now, U substitution is probably the most important tool that you can use when you're integrating, and you're probably going to do it like 95% of the time. So all these problems that you did in the previous sections regarding they didn't require U substitution and they weren't too complex to solve. But this is a very powerful tool right here because as I've mentioned before, with derivatives, we had those few rules, right? Like you had the product rule, power rule, quotient rule, chain rule, and you could derive any kind of function with that. But with integration going in the reverse direction, it's very difficult. There's no set of rules that will allow you to do every kind of integral possible. But this U substitution does let us work out many more integrals or find the antiderivative of many more types of functions. What is U substitution? Okay, so here's the rule. So it says if U equals G of X is a differentiable function whose range is an interval I, and F is continuous on I, then we can say this. We can say the integral of F of G of X times G prime of X dx is equal to the integral of F of U du. So what does all this mean? You see, oh, F of G of X times the derivative of G of X, and all that's equal to F of U. What does all this mean right here? Well, maybe you're realizing, oh, there's a U right there. There's the U substitution. So basically, what are we trying to do right here? Let's see. Let's take a look at a problem where we would need U substitution. So now, why would we want to use U substitution right here? Well, one way of doing it, an extremely long way, is we could sit here and multiply this out 5 times, right? That'd be FOIL 5 times, then distribute the x cubed in. But that would take forever, right? Remember, this is not just saying, oh, 2 to the 5th, x to the 4th to the 5th. You have to write it out 5 times in FOIL. That would take too long. But with U substitution, what we can do is normally you have something trapped inside of something else. Or what you want to ask yourself is, what can I let U be so that when I take its derivative, it matches something else in the integral? Okay, so that's what you always want to think with U substitution. Again, it's what piece of this can I take the derivative of so that when I take that derivative, its result is something else that matches in the integral. So when I'm talking about that, I'm looking at two different things, like maybe it's this, or maybe it's this right here. So what you're thinking is, well, if I take the derivative of the blue thing, what's left over, will it match something else in the problem? Or if I take the derivative of the red thing, the x cubed, will it match something else that's in the problem? Well, the answer is this right here, okay? We're going to let U equal 2 plus x to the 4th. Why? Because if I take the derivative, so when you do this, the steps are very important. If I take the derivative of this piece, what's left over? 4x cubed. And since we're deriving with respect to x, we're always going to have a dx. That's very important whenever you do u substitution. Now, what just happened right here? Well, when I took the derivative of u, remember we're trying to think, what can I take the derivative of so that its result matches something else in the problem? Well, look what matches right here. This, right? We needed an x cubed because that is also in the problem. So that's the ultimate goal of u substitution. You're just choosing a piece of something so that when you take its derivative, its result matches something else in the problem. Now, what about this 4, right? You may be saying, well, there's no 4 right here. That's right. There's a 1, right? Technically. What can you do with this 4? Well, a lot of the times when you do u substitution, when you derive something, you probably will have a constant that comes out of it. So what you can do is just move it to the other side of the equal sign. So we're just going to divide both sides by 4. So now you have 1/4 du equals x cubed dx. So what do we basically do right here? We're basically converting this integral in terms of x. We're trying to rewrite it all in terms of u. So let's see what the result is going to look like. So remember, we just said, oh, 2 plus x to the 4th is u, right? We chose that right there. So that's basically u to the 5th power, right? Because again, what's u? 2 plus x to the 4th. Now, what about this x cubed dx? So this stuff right here, what's that going to be in terms of u? It's going to be the 1/4 du. But we're not going to leave it like this, okay? We're not going to say u to the 5th times 1/4 du. We want to throw that constant out in the front. So really, we're going to have 1/4 times the integral of u to the 5th du. So what do we just do right here? Again, we started all in terms of x, and we rewrote our problem in terms of u. Now check out this integral. Isn't this one much easier to work out than what we started with? Absolutely, right? No foiling involved right here. No foiling required at all. We just have to basically integrate or find the antiderivative of u to the 5th. So let's go over again the process of how u substitution works. Whenever you're looking at these problems, you're going to have multiple parts. See how we have the x cubed part, the 2 plus x to the 4th part, like that. And sometimes you can have 20 parts. But again, the goal is you want to choose one part. You can only choose one part so that when you take its derivative, it matches something else in the problem. Let's say you let u equal x cubed instead, right? Like you were like, I'm going to do that. Well, then if you did the derivative of that, you'd get 2x squared dx. But do you see an x squared floating somewhere else in the problem right here in the integral? No. So if you choose a u and you take its derivative and it's not matching up with some other aspect of the problem, that just means you chose an incorrect u. Go back and choose another part. So again, we let u be 2 plus x to the 4th. We took the derivative of both sides with respect to x, and we got 4x cubed. Now, we know this is correct because we just needed the x cubed chunk because that was also in the integral, right? The original integral. But we didn't need the 4. We didn't need that constant. So what do? We divided it to the other side of our equal sign. And again, like probably 99% of the time, you're going to have a constant that needs to be divided over. That's how you do it. So now we have 1/4 du equals x cubed dx. Then from there, what do? We converted this whole problem in terms of x to u. So where did this u to the 5th come from? It's because, remember, we let 2 plus x to the 4th be u. So remember, this blue stuff has morphed into a u. So now you have u to the 5th. Then we had 1/4 du equals the purple stuff, right? The x cubed and the dx. So that's where this component came from. And now we move this constant out in the front. Really, if you want, you can jump from this step to this step because normally we don't say again like u to the 5th and then some constant du, okay? When you are doing u substitution, it must always be du to the 1st and the end. You cannot have du squared, du cubed, or something like that. If you do, you did something wrong, okay? This could be any power. U by itself could be to any kind of power, okay? But again, this must always be du to the first. Just like with the dx, it's always dx to the first. You've never had a dx squared, dx cubed, or dx to some other power other than 1 when we're taking the integral. Now, are we finished? No, because we need to take the antiderivative of this, right? Remember, we're trying to find out what's the integral of it. I'm going to try to squeeze it up here because I want to leave the original problem up here. So if we take the antiderivative of u to the 5th with respect to u, that's just 1/6 u to the 6th, right? Pretty straightforward. And don't forget, we need our plus c because we don't have any limits right here. But we're still not finished because, remember, our problem began in terms of x, so it needs to end in terms of x. Right here, we're still trapped with u, but we need to rewrite this u in terms of x. How can we do that? Well, we have that relationship, right? Look, right here. Didn't we say u was 2 plus x to the 4th? So now you need to convert this u back in terms of x. So this is 2 plus x to the 4th to the 6th power. And then don't forget your plus c. This is very crucial right here. You must always go back to x from u. Again, where are you going to get that relationship from? It's your initial u substitution. This will change for every single problem right here, okay? So make sure y'all do that. You can't just end it off right here. You have to go back to x because that's what we started with. All right, let's check out one like this. So we have x times sine of x squared dx. Again, this isn't a traditional integration problem, meaning we can't just integrate across. And as I mentioned with the last couple of lectures, remember, whenever you have the multiplication of two different things, right, like algebra and trig, we can't say, oh, it's the integral of x times the integral of sine of x squared. You can't separate it like that. Same thing with division. You can't split that. You can only split integration when things are connected by addition or subtraction. And in this case, it's not, it's multiplication. So again, we have to do u substitution. So there's two possibilities, right? In this case, we have maybe this, or maybe you have this right here. Or you could even do the sign. You could even say, hey, maybe the sign is another thing. There's three possibilities. There's all kinds of possibilities right here. But again, what you want to ask yourself is, what can I take the derivative of so that when I derive it, its answer matches something else in the problem? Like, let's say if you let u equal sine of x squared. If you take the derivative, what is that? Well, you'd have to chain it, right? You'd have cosine of x squared times 2x dx. Does any of this stuff exist in the original problem? Well, just the x, right? But we definitely don't have a cosine of x squared. And this 2, well, it's not a big deal. We could just move it over, but we have more junk. We don't need all this. So that just tells us, let's choose something else for u. What if we tried x squared by itself, right? The purple. So what's the derivative of x squared? It is 2x dx. Well, that's a lot better, right? Because what do we just need from the problem? The x and the dx. We have that right there. We just don't need the 2. Well, that's not a problem, right? What can we do with the 2? Just divide it over to the other side. So now you have 1/2 du equals x dx. So now we can rewrite this entire integral in terms of u. So what would that look like? Well, sine's still there. We no longer have x squared because what is x squared? It's u. And then what's the dx and the x? Remember, that's the 1/2 du, right? The blue, this blue stuff became the 1/2 du. Remember, we're not going to leave it like this though, right? This becomes 1/2 and the integral of sine of u du. Now this is way easier to integrate than this one, right? Because we no longer have two variables or an algebraic variable times a trig variable. It's just, oh, plain old antiderivative of a single trig function. So what is the antiderivative of sine of u? Well, remember, it's going to be negative cosine of u and then plus c. Remember, if you take the derivative of negative cosine, that will bounce you back to positive sine, right? Be very careful with that. So that's negative 1/2 cosine of, so remember, since we started in terms of x, we need to end in terms of x. So what was u in terms of x? This x, u is equal to x squared, right? So this becomes x squared now, and then plus c. Remember, you must rewrite the problem back in terms of x because that's what we started with. So it needs to end like that. So again, as you saw right here, I just tested the options, right? Like when I purposely let u equal sine of x squared at first just to see what would happen. And you see what happens when you choose the incorrect u. You get a bunch of extra stuff that doesn't exist in the initial problem. If that does happen, that just means go back, choose something else for u. And of course, we had to move this constant over, right? Had to move that constant over because we didn't need a 2x dx. We just needed the x dx portion right here. So here we have the quantity x plus 1 times this root. Again, nasty looking problem. We can't just integrate, oh, this times of this right here. So that's a really good indicator. Oh, probably it's going to be u substitution. And we can't pull this stuff out either, okay? Remember, we can't say, oh, square root of 2x plus square root of x squared. No, no, no. Can't do that, right? If these were connected by multiplication or division, then sure, we could separate it like that. So we have two different possibilities. This could be u, or this could be u. Which one is it going to be? Remember, you want to think, if I take the derivative of the blue, will something left over match the red? Like if I let u equal x plus 1, what would du be? That would be 1 dx. Well, that doesn't really help, right? I mean, we got that part, but what about all this? We need something to, nothing matched in the red chunk, right? Or from the red stuff. So let's try and let u be the red stuff, or 2x plus x squared. So now if we take its derivative, we get 2 plus 2x dx. Don't forget, whenever you do your du chunk, you will always have at least a dx that comes out of it. So if we look at this, initially you may think that doesn't match anything from the blue, but it sort of kind of does, right? Because what if I took half of this right here? What if I divided both sides by 2? What would you have? You'd have 1/2 du equals 1 plus x dx. Well, look at that. That's exactly what we needed, right? X plus 1 is the same thing as 1 plus x. So we have that right there, right? This is now our purple stuff right here. So now let's go out there and rewrite everything in terms of u. So what would that be? Well, this is the integral of the square root of u, right? Why? Because what's 2x plus x squared? It's u, so it's under that root right there. And then we have, well, what about the x plus 1 and a dx? Remember, that's the purple stuff, right? 1 plus x dx is 1/2 du. But this is really equal to the integral of 1/2. And This square root of u, I'm going to rewrite it in exponential form, right? Because we need to do that whenever we're taking the antiderivative or derivative. So square root of u is u to the 1/2. And now we have a basic integral, right? Look how much easier it is. When you do u substitution correctly, what's left over with your u integral, it should be way easier than what you started with. If it somehow got worse or more complicated, you definitely did something wrong. So the goal of u substitution is just to make the problem easier to work out. That's how you know I'm on the right track. Like you go from something like this, like, dang, how do I do this right here, to this is not bad, then you know you're definitely on the right track. So if we do that, if we integrate this, it's just basic power rule, right? Of antiderivatives. This is u to the, what is it, 3/2 over 3/2, right? Plus c. But then that's just 1/2. And then 2/3 u to the 3/2 plus c. And then we keep going, right? Like we can knock these 2's out. So we have 1/3. And then we need to rewrite this u back in terms of x. What is u in terms of x? There's a relationship right here. It's 2x plus x squared, all raised to the 3/2 plus c. So there's your final answer. So again, you always, it's just playing with it, right? Like, well, what should I let u be? This chunk or some other chunk? But over time, as you practice it more, you'll be able to see, oh, maybe in your head, if I take the derivative of this piece right here, will it match something else in the problem? That's all that we're looking for. And again, a really good, I guess, like checkpoint thing is after you've successfully rewritten in terms of u, it should be a lot easier to work out than what you started with. If it's harder, go back and start over because you definitely did something wrong. Most likely you chose the wrong u. All right, so let's look at this one now. So this division, again, we can't say, oh, it's integral of the top over integral of the bottom. No, can't do that with division. Can't split the integral up like that. So we have to do some u substitution right here. Well, there's really, should I let u be the top or the bottom, right? But the bottom is the only thing that really has some kind of stuff going on with it. So let's see what happens right here. If I let u equal 5 minus 3x, what's du going to be? That's just -3 dx. Okay, well, there's the dx, right, in the problem. The dx, by the way, it's always going to be in the numerator or the top part. You're never going to have the dx in the bottom for these types of problems, okay? You can't. If you somehow, you're working one out and you somehow get a dx in the bottom in the denominator at any point, then you're off, okay? So I don't need the -3, right? But that's okay. You need a 1. What can we do? Just divide both sides by -3. So now we have -1/3 du equals dx, right? So let's rewrite this now in terms of u. If I do that, what do we have? We have, oh, this integral of basically -1/3 du over u, right? So remember the 1 dx is the -1/3 u, right? Or the -1/3 du, sorry. And the u right here, that was the 5 minus 3x. Now this looks a little funky, right? We can rewrite this and say, oh, this is just -1/3 and then integral of du over u, just like that. Now, what is the antiderivative of du over u? Remember, like if we had the antiderivative of 1 over x dx, remember to the first power, it was one of those unique cases. That's just the natural log of the absolute value of x plus c, right? So this is the same concept, right? You have du over u to the first. So that would be -1/3 ln of the absolute value of u plus c. Don't forget on WebAssign, put uppercase c's, right? And then we're still not finished. because what do we need to do? Go back to x. This is negative 1/3 ln of the absolute value of, well, what's u in terms of x in this case? 5 minus 3x. And then plus c. All right, so now we have e to the x, cosine of e to the x. So again, there's all kinds of possibilities, right? You may be thinking, oh, do I let u be this e to the x, or this e to the x right here, or the cosine of the e to the x, right? What do we let u be? Remember, the goal is whatever you take the derivative of, it should match something else in the problem. Well, in this case, the red and the blue, it's like the same thing, right? So you may be thinking, what do we do? Well, I'm gonna use the blue marker to signify I'm letting u equal this e to the x right here. So if I take its derivative, guess what? What's the derivative of e to the x? It's e to the x and then dx. So now, if you notice, I purposely chose the red. Why? Because when we derive this blue e to the x, what was left over? The e to the x on the outside and the dx component right there. So what does this look like if we rewrite it in terms of u? Notice too, we don't have a constant in this case. I don't need to divide anything over, right? So we were lucky in that case. So if we rewrite this in terms of u, what do you basically have? You just have cosine of u du. Now you can always double check this, right? You could say, you can ask yourself, did I rewrite this correctly in terms of u? How can you do that? Work backwards. What if I plug in u back in terms of x? What do I get? I get back to cosine of e to the x. What if I plug in what du was in terms of x? What do you get back to? The e to the x, d to the x, right? So if you work backwards, you can always substitute back in these values that you did a relations back in, and you should be able to get back to your original equation. So now, what is the antiderivative of cosine of u? It's just positive sine of u, right? Plus c. Remember, how can you check your antiderivative? If you take the derivative of the antiderivative, it should bounce back to what you are or initially started with. Are we finished right here? No. What's missing? We need to go out there and rewrite the u in terms of x. So this becomes sine of, and what's the relationship between u and x? It's this, right? So we have sine of e to the x plus c. All right, here we go. Now we have one that looks a little more tricky. It's division, right? Again, we can't go out there and integrate the top and then integrate the bottom, right, separately. So that indicates, oh, I got to do u substitution. So there's two possibilities, right? Do we let u be this thing, or do we let u be this right here? Which one is it going to be? So remember, the goal is to, you want to, again, think, if I take the derivative of the purple stuff, or natural log of x in this case, will the result be something else that's in the problem? Or if I take the derivative of the denominator, will its result be something else that's left in the problem? I mean, like, what if we let u equal x? What's du? Well, that's 1 dx. So that's takes care of the dx. What about the ln of x, right? That doesn't help. So let's go back and try the other one. What if we let u equal ln of x? What's du going to be? That's 1 over x dx. Well, that's great because look at this 1 over x. Where is that happening? Right here. This is ln of x squared over x. So this is perfect. This is a perfect fit. Now, what does this look like in terms of u? Well, remember, u is ln of x. We have ln of x squared. That would just be u squared. And then du. That's it, right? Because look, what is du? It's the 1 over x component. I mean, in theory, you could say this is 1 times this ln of x square stuff over x. So there's the 1 over x and the dx. That is the whole du right there. So we went from some really crazy, hard-looking problem to something basic, right? Because what is this? This is 1/3 u cubed plus c. But then to finish it off, what do you need to do? Rewrite it in terms of x. So this is 1/3 ln of x cubed plus c. And there you go. What about if we did something like this right here? Like, what's the integral of tangent of theta d theta? Just like that. Antiderivative of that. How can we figure that out right there? Well, remember with trig functions, if you ever lost or don't know where to start, rewrite them in terms of just their base form, which is some kind of sine and or cosine. Well, this is definitely like that, right? We could say, oh, this is sine of theta over cosine of theta d theta. So now we have two different pieces, right? That's a little better. So right here, there's a couple different things we could try, right? We could say, oh, let u equal what? The top or the bottom? Remember, the goal is you want to think, if I take the derivative of something, will it match something else in the problem? So if I let u equal sine of theta, what does du equal? Well, du would be cosine of theta d theta. So what can we do from here? Well, we kind of have an issue, right? You have to be very careful because you can't just sit there and go, oh, there's a cosine of theta here and a cosine of theta here. I'm good, right? And then we could say, oh, this is just the integral of u du. This we cannot do. Why? Because in order for this u substitution to be valid, this cosine of theta would have to be in the numerator, okay? So can't do this one. Cosine of theta needs to be in the numerator. Now, if you took the derivative of u and somehow this shifted into 1 over cosine of theta d theta, then yeah, we'd be okay right there. But in this case, we're not, because again, when we took the derivative, the cosine of theta still wound up in the numerator. If your problem was like this, then yes, this would be a perfect u substitution because this cosine and d theta appear in the numerator. So since that does not work, what do we need to try out? Well, let's let u be cosine, right? That's the only other piece. If we let u equal cosine of theta, what's du going to be? That would be negative sine of theta d theta. We just don't need the negative, right? Because we just had a positive right here. What do? Divide it. So now you have negative du equals sine of theta d theta. Now, if we rewrite this in terms of u, what are we going to have? Well, that negative, I'm just going to take it out in the front. And we have the du up top. Remember, du, the negative du component is the sine of theta d theta. And on the bottom, what do we have right here? U, right? Why? Because what is U? U was cosine of theta. This we can integrate, right? Remember, this is like that 1 over a variable to the first power. What's the antiderivative of that? That's a natural log. So you get negative natural log of the absolute value of U plus C. What is that? Or how do we finish this off? We have to go back to theta, right? We're in U right now. We need to go back to the variable theta. How do we do that? What's the relationship between U and theta? It's right here. So it's actually negative natural log of the cosine of theta plus C with your absolute value bars. All right, so now we have the product of two different trig functions right here. So what can we do, right? It's kind of tricky. Where do you start with this right here? You may try trig identities, right? Rewrite secant squared in terms of tangent or tangent in terms of secant. What you, again, the ultimate goal is you just need to ask yourself, what can I take the derivative of so that result matches something else in the problem? So remember, what's the derivative of secant x? That would just be a secant x tan x. So I mean that kind of helps out, but we have this tan cubed, right? Which makes it more complicated. We need a cubed right there. So that doesn't really work. What if I let u equal, say, tan x? Du equals secant squared x dx. That's kind of okay too, right? Because look at it. We have a secant squared. We have a tan x right here. This is tan cubed. Well, this is it, right? What happens if I take this and I rewrite it in terms of u and du? Well, if you have tan cubed and u is equal to tan to the first of x, well, that means you have a u cubed du. Check it out, right? Because look, u is tangent. If I have a cubed of it, it's u cubed. The du is the secant squared and dx component. So now we have something very straightforward to work out. This is just 1/4 u to the fourth plus c. And of course, we go back to x. This is 1/4. And then tangent of x to the fourth, or I'll say tan 4 of x, and then plus c. Really important when y'all write this in WebAssign, don't put tan x4. This right here is not equal to this. This is saying the x is raised to the fourth. This 4 is saying the tangent is raised to the fourth. So do not type it in like this. That's two different functions, okay? All right, look at this one. Now we have e raised the tangent of x, secant squared of x dx. Messy looking problem, right? But again, just ask yourself, what part can I take the derivative of so that its result will match something else in the problem? So again, you have a couple things. You have this. You also have this right here, right? And you could even say, you could even do this, right? We could even do that right there, derive that. So there's three different things we could derive right here, but you want to ask yourself which one will, so that when I derive it, its result will match something else in the problem. Like what if you let u equal secant squared of x? What would du be? You'd have to chain this, right? You have to do the outside first. So you'd have 2 secant to the first of x times the derivative of secant of x, which is secant x tan x. This doesn't help at all. We don't even have another secant x or secant squared x and a tan x floating outside right here. This, let's say even if for some reason you were just left with a tan x, You cannot say, oh, that works out because of that tangent right here. No, that tangent is trapped inside of the exponent right there, so that still wouldn't help you out. So this is definitely not the correct u. What if we let u equal the blue, tan x? What's its derivative? It's secant square root of x dx. Ah, there we go, because that matches the purple, right? Look, that's exactly what we needed. So if we rewrite this in terms of u, what do we have? It's still e, but this time is to the u, right? Because tangent, we let u be tangent of x, and then du, right? Because what is du in this case? The secant squared x. So now look, something very easy. What's the antiderivative of e to the u? E to the u, and then plus c. But to finish it, we have to go back to x, right? So e raised to the tangent of x plus c. All right, so division, right? So you may be thinking, oh, possibilities for you, maybe the top or the bottom. Well, let's see. If I let u equal the bottom, right? Let's see what happens right here. Oops, don't need this. If we take the derivative, you get 2x dx. Now, we need the x dx component, but what about that 1 plus? You need that. You definitely need that 1 to pop up right there. So we can't use this as u, okay? What if you let u be the top? This doesn't help either because now you just get dx. So it matches that. What about the whole denominator? What do we do right there? Well, sometimes we just have to completely rewrite the problem. All right. Kind of like with stuff where in some instances we had a FOIL, right? Or use a trig identity, something like that. We're going to do that right here. We're going to break this up into two smaller integrals. This we could say is 1 over 1 plus x squared dx plus the integral of x over 1 plus x squared dx. Is this legal right here? Yeah, right, because if I add these back up, remember, how do you add up fractions? If you have to make sure that the denominators are the same. They are, right? Look, if the denominators are the same, we add or subtract the tops. So if I add back these two together, what do you get? This, right? So we just rearranged the problem or rewrote it. Now, why did I do that? Because now both of these are very straightforward integrals. Remember, this one, it looks tricky, but this is one of those arc functions. I mentioned it in the last section. If you have the sum or difference of squares in your denominator and you're taking the antiderivative, there's a good chance that you're going to have some kind of arc trig function. And this is arc tangent right here. So this one's done. That was it right there. What about this one right here? Well, we can let u equal 1 plus x squared. Why? Because what's du? That's going to be 2x dx. Well, x dx, x dx. That's what we needed, right? We just need to move the 2 to the other side. So now you have 1/2 du equals x dx. So don't forget this right here. I'm just going to erase it because I need the space. So now if we write this in terms of u, what does it look like? It just looks like 1/2 and the integral of du over u. Remember the 1/2 du, what is that equal to? The x dx component. That u in the denominator, where's that come from? It's because we let u be 1 over or 1 plus x squared. And then what's the antiderivative of du over u? Remember, that is ln of the absolute value of u. So you have 1/2 and ln of the absolute value of u plus c. But then if we rewrite it back in terms of x, we have ln absolute value of 1 plus x squared plus c. But over your final answer has that arctangent as well, right? So we had arctangent of x plus 1/2 ln of 1 plus x squared plus c. All right, so here we go. Now, if we look at this one, it's kind of weird, right? So again, you're multiplying two different chunks. We can't split it up into two smaller integrals. So again, you got to be thinking, if I take the derivative of one chunk, hopefully it'll match, the result will match something else in the problem. And you have two chunks, right? Like you have the x and you have the stuff inside the root, right? So it's kind of weird because if I just let u equal x, the purple stuff, du equals dx, well, that doesn't really help out because what about the x minus 1, right? So that doesn't work. What if I let u equal x minus 1? Now the inside, du equals dx. Well, that still doesn't help because what about this x component right here? So what we have to do is a little bit of manipulation, all right? Now, what I mean by that is we are going to let u equal the x minus 1, or the bigger part. Basically, the u in this case was the part under the trickier component to deal with. I say trickier component because roots are more difficult to deal with than algebraic expressions, like x to the first, and there's also more terms under here. So why did I do that? Well, I can rewrite this, right? What if I said u plus 1 is equal to x? Why did I do that right there? Well, let's see what happens if I rewrite this integral. And then also, what would du be in this case? Du is equal to just dx, right? I'm deriving this right here. What's the derivative of this? Du is just equal to 1 dx. So let's see what happens when I rewrite this in terms of u, or a bunch of u's. So this x component, what is that in terms of u? The purple. Well, when I did this manipulation, right, look, x is equal to u plus 1. So I could say, oh, that's u plus 1. So remember, u plus 1 has morphed into x. How do we do that right there? Because again, we let u equal x minus 1, the stuff with the most terms, and I solved it. I rearranged it for the x component right there. I just added 1 to both sides, right, and got that. Now, what about the blue right here? What's that going to be? That's going to be the square root of u, right? Why? Because what's the blue? Blue was x minus 1, or u, like that. And now we have our du. Remember, du in this case was just the dx. So we're good right there. So this one was kind of tricky, right? How do we know that we need to do this right here? Well, normally when you have to do these kinds of tricks, your x's are located inside of two different types of functions. Like this is an algebraic one, this is inside of a root, and they're both the same power, right? They're both x's to the first. So to the same power, and that's kind of a good indicator. You have to do this trick of, oh, whatever I let u be, I'm gonna have to solve it for x, and then rewrite that other x that's floating outside or whatever in terms of that u component like that. Now we're still not finished, right? Because we have to integrate. How do we integrate this thing? Well, remember, this just becomes the integral of u plus 1 times u to the 1/2 du. Remember, we want to convert this into root form right here. And then we're going to distribute that u in, or this u to the 1/2. U to the 1/2 times u to the first is u to the 3/2. Plus, what's u to the 1/2 times 1? U to the 1/2, and then du. And then let's go ahead and take the antiderivative, right? The antiderivative of u to the 3/2 is u to the 5/2 over 5/2, which is 2/5 u to the 5/2, right? It's just the power rule. Plus, the antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2, or 2/3 u to the 3/2, and then we have plus c. Are we finished yet? No, because we have to go back to x. What's the relationship between u and x? This right here, u equals x minus 1. So you're going to have 2/5 and then x minus 1 to the 5 halves plus 2/3 x minus 1 to the 3 halves plus c, just like that. All right, so let's try another one like this, right? Because these are probably the most complicated ones because you have to do that manipulation between u and x right there. All right, so again, if you wanted to, you could FOIL this out 8 times, right, and avoid the use substitution, but no, it's not gonna happen. So, because again, it would just take forever. There's that one we're gonna do that manipulation trick that we just did. Why? Because they're both x's to the first, and one's trapped inside this crazy glob of stuff. Now the trick was to let u be the one with the most terms, so that would be this guy right here. And let's find a du really quick. Du is equal to 2 dx. Remember, we didn't need this 2, so we just divide, both sides by 2. So then you could say, okay, we have 1/2 du equals dx. Now, what about this x to the first, right? Because when I took du, we didn't have an x just floating out right here. So what do we have to do? Take this equation and manipulate it for just x. So how would we take this and solve for x? Well, you'd say, oh, u minus 5 equals 2x, right? Divide by 2. And then you get 1/2 u minus 5 equals x. So let's go out there and rewrite this whole integral now in terms of u. What would that look like? So we still have this 1/2 integral of. Now, what is x in this case? Remember, x we said was this 1/2 u minus 5 component. And then what's the 2x plus 5 become in terms of u? That was just u, right? So we have u to the 8th power du. And from here, now we can go out there and solve this, right? We can distribute. So I have 1/2 and then an integral of u to the 9th minus 5u to the 8th du. And I'm just going to go up here now. So now if we take the antiderivative of both of these pieces, we get 1/10 u to the 10th minus 5/9 u to the 9th plus c. And then we're going to distribute the 1/2 in and rewrite it back in terms of x. So we get 1/20. And then what's u? U was 2x plus 5. So 2x plus 5 to the 10th minus 5/18. 2x plus 5 to the 9th. And then plus c. So again, let's go over what we did in this problem and why we had to do it. So how do we know we have to do all this manipulation stuff? Well, it's because, again, we have two x's. They're trapped inside of two different things, right? Like this is just an x all alone by itself, not really trapped inside of anything. And this one's trapped inside of the 8th power. This could be like inside of a root, right? Or some other thing. And they're both the same power. And there's a problem, right? Because if we let u just equal either one, the x or the 2x plus 5, the d is not going to, or the result is not going to match up the other part of the problem. So what we have to do is manipulate one piece. Usually you want to manipulate the piece with the most terms, right? Like I can take this 2x plus 5 and I can solve it for x. I can't take this x piece and somehow solve it to make it look like a 2x plus 5, right? We can't do that right there without doing illegal math. So we take the piece, the larger piece with the most terms, and we rearrange it for that sole x, right? That's what I did right here. And of course, when you do this process, this little trick, when you find your u, don't forget to take your du, right? And move any constants over to the other side, like what we did right here. And then once we've successfully isolated our x, like what I did in the purple right here, we can rewrite our initial problem in terms of u. Or we can check all this, right? Like if I take all this and I rewrite it back in terms of x, what do we get? Well, remember, what is all this purple junk equal to? The 1/2 and the u minus 5, the x. That's what we had. What's this u equal to? The 2x plus 5, the 8th, like that. What's that du equal to? We saw it. The dx, or the 1/2 du, sorry, like that. And then from there, we're able to integrate, right? We're able to successfully integrate that thing right there. I think I forgot something. Ah, yes, I did. So this 1/2 right here, we also need to multiply that 1/2 in. I forgot to do that. So I'm going to put that in red, and we're going to have another 1/2 right here. So this is going to be a 4th right here. This is going to be a 4th. This is going to be a 40th. This will be a 36 right here. All right, so where did this 4 come from? Where did this extra 1/2 come from? So this purple 1/2 came from us isolating this u right here. This red 1/2 came from us moving the constant over when we did the du, when we went from u to du. So I had to bring over also that additional 1/2. Any of these constants that you're always bringing along like this, you will multiply. So make sure you watch out for that right there. So I can change all these. Sorry about that right there. So this will be part 1. I'll do a part 2 where we have limits, right? Like numbers on the inside. It doesn't really change. It's just more work. In the end, it's just that you have to evaluate, right? And plug the numbers in, and you would no longer have a plus C.